This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Okay, this afternoon session is on energy and sustainability. I'm Lisa Schaefer. I have known Charlie for 20 years. I'm one of the people who met him when he first came to NASA. I was running the international office for Mission to Planet Earth when Charlie came in to be the associate administrator. And in the last 20 years, we've spent a lot of time traveling the globe together. I put together a few pictures of travels with Charlie that'll just run in the background while I'm saying a few words. So first, I wanted to thank Ellen for organizing this event with Charlie, but more important, for being a wonderful partner for Charlie, at least through the 20 years that I've known them. I think that much of his success is due in part to your support for him. The thing that distinguishes Charlie from many other people I've known is that he has a huge intellect and a small ego. And as Ray Weiss said very eloquently earlier, he really combines a sense of generosity and curiosity, and has taught me many lessons in the time that we've spent together. One of the things I noted when I was trying to recall all the things that we've done is that there's very little that I could say that was specifically, Charlie and I did this, because everything was a joint effort with many other people and much shared credit and shared participation. Charlie has a style of management that really empowers everyone to be and do the best that they can be and do without worrying about who gets credit for it. And I'm very grateful for that. And if it weren't for Charlie, I wouldn't have moved to San Diego. He recruited me here from NASA. I wouldn't have met and married my husband, who's up there on the balcony, and a lot of things would have been different in my life. So I owe Charlie a lot for the improvements he's made in my life. So when we were at NASA, we already had a committee on Earth observation satellites with all of the space agencies that had Earth observing programs, and he recruited me to come here to Scripps to create a similar organization for the oceanographic community, which became POGO, the Partnership for Observation of the Global Oceans. And we set that up with... You get credit. Okay, I get credit for the name. And we set that up with Woods Hole in Southampton initially, and it is an ongoing organization. At NASA, the Committee on Earth Observation Satellites still exists, and it became the foundation. Charlie really re-energized it into the integrated global observing strategy and the system of systems, and the whole concept of networks and systems is something you've heard a lot in the last day and a half. After I got to Scripps, some of the things that we worked on together, which you've also heard mentioned already, we set up the UC Revell program on climate science and policy. Lisa Levin mentioned the students who went to the climate negotiations this last year. Actually, we sent our first delegation in 1998 from the University of California to the climate negotiations that year in Buenos Aires. Chris Mazel is here, who was part of the delegation to The Hague in 2002, so we still have accreditation for the whole UC system to send delegations to the climate talks, and that's been a very wonderful experience for all the people who've been involved in going to them. I was part of helping create the Center for Marine Biodiversity and Conservation. You've also heard about a lot. I think I'm the first political scientist at the podium in this forum. We'll have another one in a few minutes. And I also have an MBA, so I brought a little different perspective to the things that we were doing, but I served as kind of the ambassador to the main campus from Scripps and helped build some of the relationships between Scripps and the departments of economics and political science and international relations and the business school. And then when Charlie's term as Vice Chancellor ended and the Chancellor said, go build an environment and sustainability initiative with no resources, he turned to me and said, well, now what? And we said, well, let's go do it. And so we did, and we created the Environment and Sustainability Initiative, which then became the Sustainability Solutions Institute. It became the home for a number of interdisciplinary activities for a variety of reasons. I don't think it exists anymore, but it was a starting point for a lot of cross-campus interaction that has become very fruitful. So as I said, Charlie changed my life for the better. He's also changed the world for the better, and I'm very grateful for that, and happy birthday. So getting to our panel. An astronaut, an atmospheric scientist, and an energy wonk go into a bar. Oh, no, sorry, that's not what I'm supposed to say. This session will be presented by an emeritus MIT physics professor who's an expert on fusion energy.
I'm not emeritus.
Excuse me?
I'm not emeritus.
Oh, I'm sorry. By a current MIT physics professor and fusion energy expert. A political scientist who's the author of a book called Global Warming Gridlock and runs a laboratory on international law and regulation at the UCSD School of International Relations and Pacific Studies. A former astronaut who is now a professor at Carnegie Mellon University and directs their electricity industry center. Did I get that right? And a distinguished professor at Scripps who is one of the discoverers of the greenhouse effect of halocarbons, who helped design cooking stoves and serves as a member of Pope Francis's Council for the Pontifical Academy of Sciences. I'm a political scientist who taught business ethics, and I now serve as a city council member in the city of Encinitas, just up the coast. So this is truly an interdisciplinary panel in the super interdisciplinary, or somebody had a phrase yesterday, mega interdisciplinary? Hyper interdisciplinary panel. Sorry. So our topic, energy and sustainability, kind of sums up our challenge. Energy is central to life, and our patterns of energy consumption and production have put us on an unsustainable path for the future. And you've heard the John Muir quote about how if you tug on a string anywhere, you find that it's connected to everything, and certainly energy is connected to everything. So we will cover the role of government, the energy technology outlook, and the nexus between population, poverty, consumption, climate change, and the bottom of the pyramid, or those most impacted. Somebody reads slow, I guess. Those those most impacted when we don't get it right. So we're going to start with Professor Ramanathan, who will discuss the bottom 3 billion who have limited access to fossil fuels, yet they are the population that will be most affected by climate change resulting from fossil fuel consumption by the top 1 billion. I'm going to introduce everybody, and then I'll give you the microphone. So I'll introduce everybody, then they'll each talk, and then we'll do questions at the end. Ram will be followed by David Victor, who is going to talk about the role of goals in environmental governance and continue the discussion Charlie started before lunch about whether the goal of limiting warming to 2 degrees is the right goal, why are some areas of sustainability governance working well and others have failed, and what the scientific community can do to help. David will be followed by Jay Apt, our astronaut, who will present his views on the prospects for low-carbon electric power generation, focusing on the U.S., what are realistic expectations for wind and solar, given issues related to land use. As a local government official, I now appreciate more than ever issues of land use. How much energy do we need? How can we get it in a sustainable way? What role will CO2 capture technology play to enable the continued use of fossil fuel plants? And then Bruno Coppi will summarize the energy challenges and some possible solutions as seen by his energy group and lead us into our discussion with the audience. So each presenter will have 10 minutes, and then we'll hold all the questions until the end and have a very lively discussion. So with that, it's a privilege to introduce Professor Ramanathan.
Thank you, Lisa. I have an experience with Charlie, which I think is unique. When he stepped down from a director of Scripps, I think I was one of the top beneficiaries of that. He moved into an office around the corner from mine, and that started a collaboration. which has been really exciting for me. And then I had the fortune to collaborate with people like Ralph Cicerone, Crutzen, Mario, and now Partha Dasgupta. And Charlie's is way up there. And I'll show you some examples of that, so I'm not going to get into it now. I thought we didn't really discuss mitigation. So that's why I requested Lisa to put me first. I've changed the structure of my talk a little bit. The first thing is I'm trying a new approach in this. So to just introduce, I really see there are two separate worlds in this planet. First is the top 1 billion. Of course, all of us belong to that group, living as if there is no limit to fossil fuel access. Contrast that with the bottom 3 billion, like that woman who's cooking. I'm going to talk to you about her in the Himalayan village. There are 3 billion like her who have no access to fossil fuels. They're still burning firewood and biomass, coal, etc. And yet, they will probably be the worst sufferers of climate change. And I'll give you some statistics of these. So given that background, I'm going to come back to that last, but let me dive into the mitigation issue. Any theory should be judged by the prediction it makes. So in 1980, I teamed up with the famous meteorologist Roland Madden. He was not that famous then, so he worked with me. And he was an expert in understanding natural variability in the system. So I asked Raul the question, when is the signal going to exceed the variability? So he said, you predict the signal, I'll estimate the variability, we'll figure out. So it's a complicated statistical dynamic. So we concluded that the warming, if the theory is not flawed, seriously, it should be detectable by year 2000. Of course, you have seen this many, many times. And we published the paper. We started work on it in 1977, finished it by 1980, when the system was still cooling, or the so-called hiatus. And you can see in 2000 is when it really rose above the noise, and that was recognized by IPCC. That prediction from the model was several things had to work right. It's just not simulating temperature, because the whole climate sensitivity is determined by the water vapor thermodynamics. And we also include the sea ice feedback. Otherwise, we wouldn't have got which Peter Waltham showed. So many things had to go into that prediction. So using that as my credibility for making forecast, we published a series of papers, 2008 and 2010. Both of them had the benefit of, this was about the time Charlie stepped down. And he and Larry Smarr gave some tremendous comments on the paper, which really changed the way that paper finally was published. So what I deduced in those papers, basically my students and postdocs, we have already dumped enough greenhouse gases to warm the planet by 2.5. This deduction was there in all IPCC, but they never came to that conclusion. Okay? So what that means is that if you cut the emissions of CO2, we are still going to meet the 2.5. All right? And I'll tell you how to get out of that. The second is, everyone was thinking climate change was 100 years, 200 years. We came with the bold prediction that, the forecast, that we're going to see the 2-degree warming not end of the century, 40 years from now. And now this has been supported by numerous other climate model studies. So the point is, it's still not too late. So let's see how we can do that. So the first thing we have to recognize is that CO2 is not the only lever we have to bring down climate change. So how long have we known that? Svante Arrhenius was the first quantitative estimate of the CO2 effect in 1891. For nearly 100 years, the books were written as if CO2 was the only pollutant we are putting. So I accidentally stumbled onto this discovery. Until this point, my work was on Mars and Venus. I was studying radiative transfer in CO2 atmospheres. So that was my entry into the Earth's atmosphere. And I was shocked to find, in fact, when this paper was published, it was ridiculed because it got into the front page of New York Times. You know what that means. It gets your colleagues all upset with you. It took them 5 years to figure it out. So the CFC, as adding one molecule, has the same effect as adding 10,000 molecules. And you saw in Ray Weiss's host of such synthetic compounds had been released. So why is that CFC so effective? First, its concentration is so low that when you increase it, its absorption increases linearly. CO2, there's so much of it. When you increase CO2, its greenhouse effect increases logarithmically. The second more important reason is this has absorption bands. All this absorption comes from the vibrational and rotational freedom of the molecule. Happens in the 8 to 12 micron region, which is nearly transparent. In fact, it's the only spectral region the planet has to ventilate its heat from surface directly it goes to space. These synthetic molecules are plugging that window, so that's why they're so potent. So quickly, now going back to 2013, this whole non-CO2 has become a huge problem. So if you look at the current warming, the area of the pie is proportional to the watts per meter squared. And Larry, I don't know if you recognize, he was the one who made me do it this way. That CO2 is 50%. And the other 50% comes from these various gases. I'll talk to you about BC. BC is not a gas, it's a black carbon particulate, same stuff, which comes out of diesel trucks and fires, etc. So carbon dioxide, if you just cut down its emission, even if you cut it to 0 tomorrow, that half pie is not going to be shrunk, because that heating is coming from the CO2 we emitted over the last 200 years, long lifetime. Black carbon, on the other hand, lifetime is 2 weeks. If we clean up all our diesel trucks, replace all the biomass cooking stoves with clean stoves, it's gone. It's gone in a year from now. So that's about 5 to 10% of the total warming. So we came up with this idea that is a short-term problem, slow down the warming in the immediate 30, 40 years by cutting down the short-lived pollutants. So we published this. Oh, that's in the next page. So you can see that. This is our simulation. It's the same model I had used to forecast in 1980. So the red line is what we do nothing about. So you can see you shoot past 2 degrees by mid-century and 4 degrees, and numerous other studies have come to that. CO2, the blue curve, in that model, I cut down the emission by 50% by 2015, next year. And the system takes 40 years to even know we have cut CO2 as far as the climate is concerned. Whereas the dark red line, you can see the dark line, you can see how it immediately comes down. So this doesn't mean we shouldn't do anything about CO2. CO2 reduction is to save us from the warming 100 to 200 year time scale, irreversible changes. But how do we get immediate relief? And the only way we can do that is cut down short-lived pollutants. Of course, if you follow Peter's idea, challenge Americans to suck the CO2 from the air, sure, we'll get immediate relief. Okay? So if we do it together, then we can keep the warming at 2 degrees. It's still not too late. That's the good news. So now let's talk about who's going to cut what. Yeah, I forgot to mention. Sorry. I forgot all of a sudden why I'm here, to talk about Charlie's work. And so as we reviewed this, so when this paper was come, UN called me and formed this. We wrote a report, and then Hillary Clinton got onto it, formed the Climate and Clean Air Coalition in 2011. But Charlie saw this curve and said, my God, that means we have to adapt. Nothing we do is going to keep us even at 2 degrees. So he combined this science with his instincts for institutions, and then we brought in our political scientist, David Victor. Before this, David and I had written an op-ed in New York Times. It was before the 2009 Copenhagen meeting. That caught the attention of this. So these are the 2 papers which put this whole thing together. Okay? And what I found with this He said, it took me after this paper. I said, I'm going to wait another 2 years before I start collaborating with Charlie. He is one of the most incredibly efficient and productive and creative scientists I've met. I'll talk to him, we meet for lunch, and within a month, the paper will be there. So that's how fast Charlie was. And I had to do very little to edit it or change it. Anyway, going on, so the CO2 problem. Who should do something about it? So I've broken the CO2 emission by the population. Okay, the 1B is 1 billion. You can see, focus on 2000, half of the emission comes from just 1 billion super emitters. The bottom 3 billion, I remember saying they don't even know fossil fuels are around, have been invented. Okay? So how come they still have 1.9 tons? Because they're cutting down forests for cooking, etc. What is most disturbing to me is that the increase projected, these numbers, the way I've talked about it is mine, but basic numbers come from two groups, one from Princeton, another from YASA. The increase, half the increase, comes from the top 1 billion. So the CO2 problem is just not a population issue, it's a consumption issue. 2/3 of the increase coming from increased consumption, okay? And the bottom 3 billion are still there. What is interesting is this top 1 billion, you may immediately think it's all Western, US, Europe, of course majority, but they're everywhere in the world. I have a video which shows how in India, the top 1 billion and bottom 3 live side by side. So this sort of takes the debate away from national issues, brings down to the people. So let's go to the bottom 3 billion world. I was living beside this woman's home, I'll show it. So I told her, Dina, the smoke from this is melting Himalayan glaciers. She laughed at me. Oh, you're Indian, you've gone to America, you bring all this fancy science. So I took her outside. I showed her how that smoke from her house, that's mainly a lot of black carbon. And then I was living in the similar house, but a couple of 100 yards behind her. I whipped up my satellite and laptop, and that shocked her. So you can see, because there were 150 million such homes, okay? This is what we call atmospheric brown clouds. It causes 4 million deaths around the world. Not this pollution, people like this cooking. Destroys millions of tons of crops from the ozone and sea carbon monoxide. My own work showed black carbon is the most efficient absorber of sunlight there is in this planet. That's why it's called black carbon, okay? And it disrupts the way sunlight is distributed. How do we know this? So this was a new platform was designed in my lab just by graduate students and postdocs. I want to make my colleagues here from Cambridge University and Harvard jealous by saying we get some of the best young minds here. So they designed all miniaturized these instruments. We captured this 3-kilometer plume within the aircraft. So we could measure everything, what's going in, what's going out. And that's how we know black carbon is the second largest contributor to global warming. I forgot to mention an important detail. How do I know that smoke? Where is it coming from? Could be diesel trucks, could be cars. We have another remarkable scientist here, Kim Prather, I don't know where she is. She joined me in one of these campaigns and used her instrument. She did use 70 to 75% of that black carbon is coming from biomass burning. That's what we know. You solve the cooking problem, you have solved the Himalayan, at least half of the Himalayan glacier melt problem. So we started this program, Project Surya. Surya means in Sanskrit, solar. And I trained the help of my daughter, Nitya, who is a wireless technology expert. So she designed cell phone sensors to measure mass measurements in a lot of the homes. So we tested various cook stoves and figured out which one brings down. Basically, the cook stove we come up with, you see there, it basically has a gasifier inside. So you ignite the firewood at the bottom, and the unburned gases goes up, and we reignited at the top. and we make the airflow by having a fan. Mind you, there's no electricity, so the fan was charged by solar. But there's a problem it was too expensive, $70. Their average take-home pay is $1 per capita, okay? So that's about 8 weeks of their paycheck. It's 8 weeks of paycheck was the solar in my house, and I couldn't do it till all my children graduated, right? So the women have the same problem. So how do we solve that? So we came with the idea, if we can provide them carbon credit for cutting down black carbon, mind you, it's the second largest contributor to global warming, or for cutting CO2 emissions. But the question is, how do you know they're using my stuff? We wanted to give the carbon credit directly to the woman. So I went back to my daughter. So every time I have a problem, I tell her, why don't you do something useful? So she came up with the way to monitor each cook stove. And so you can see, this matrix you see, each column is individual house. Each row is a day of the month. So if she gets continuous data, you can see how when the woman cooks, that goes up, the temperature comes down, evening shift goes up. Half the time we wouldn't get the data because the women wouldn't charge the cell phones. So she started monitoring the cell phone battery too. If the cell phone battery is gone, the woman would get a text message from my daughter at Los Angeles. She goes, charges it, okay? So University of California, we had generous donation to this program from Charlie and Ellen, and we persuaded a billionaire to fund us for 5,000 homes. We are trying this climate credit. So the money would go. So that data would come to my lab. I would convert it into climate credits. Then we'll call the carbon market to see the price, not the CDM, but voluntary. Then send them check. Okay? So we just started this 3 months ago. In another 6 months, we're supposed to have all the 5,000 homes. So what should we do? Clearly, all this talk about decarbonizing renewables are really applied to the top 1 billion. And what is the cost of that? Estimated IPC is $1 trillion divided with $1,000 per capita per year. And the fossil fuel subsidy alone is $525. So it's a $450 problem per capita, okay? In addition to that, we should provide renewable energy access to the bottom 3 billion for our own preservation. If they go on the fossil fuel ladder, their emission would go by about 14 billion tons. Remember, right now we are about 35. We'll go to 50 by 2030. We need to bring it from 35 to 17. If this new group is going to join our club, so it's for our own benefit, we give them. And here, I think we may hear from Professor Jayab, the so-called mini-grid is offering tremendous potential. And I don't know if you know, UCSD has the largest mini-grid system with renewables. And we are teaming up with them. So come up with this idea of using solar, crop waste, and biomass to provide electricity and gas. So this is a little bit complicated, both for the basic needs and productive. So we are now going to propose it. I'm teaming up with some energy technologies at Berkeley and India. And we are trying to do it in a home of about 20 villages to really understand how does it change people's lives. How does it change the pollution in these villages by giving them renewables? And by the way, these kind of technologies are already available in the villages. It's just spreading like wildfire. So last, I want to end with this. Clearly, I'm now teaming up with a well-known economist at Cambridge University, Sir Partha Dasgupta, development economist. He has written an enormous amount about this. Talking with him, I got persuaded this whole thing is not going to happen unless we change our attitude to each other. You saw the top 1, bottom 3 billion. And attitude towards nature. So we proposed this to the Vatican with the blessing of the Pope. We got together a remarkable group of scientists from here. Professor Rees, Charlie Kennel, Monk came to that meeting. At the end of it, and you see next to me is Partha Dasgupta. And there's another thing amazing about this story. You all think Catholic Church, it's mainly, denominational. Neither of us are Christians, yet we play an important role in the church. It's purely non-denominational group, this Pontifical Academy of Science. And we're able to brief the Pope after that. And after this meeting, he has released many, many statements, powerful statements about sustainability. Thank you.
I just want to say that you can go ahead and take this. When Ram participated in one of our early UC Ravel programs, he had just done some of the analysis. He talked about where you analyze the chemical composition of the black carbon particles, and you could say this much came from industry and this much came from biomass. And we had economists from the World Bank, and they said, well, are they stationary targets? Are they moving sources? And he said, well, we don't care. We just do the chemical composition. And he was very proud of the science, and the science just stood alone. And over the last 15 years, you can see how all of us have evolved in our understanding of the interconnections of these things, where it's not enough just to do the science, but we have to figure out what it means and how to use it to make change. So I'm delighted to see that.
Thank you very much, Lisa. And it's terrific to be here and to honor Charlie's birthday. My name's David Victor. I'm, I guess, the other political scientist. I'm a little skeptical of a panel that has all the political scientists concentrated in one place right after lunch. I think the only thing that could have made it worse is serving alcohol at lunch. But I came here about 5 years ago from Stanford University, and Charlie was one of the people who welcomed me here, and I'm just enormously grateful for that. I think because as a political scientist, my instinct has been to wander around other disciplines, and I'm just keenly interested in the climate issue and with the work here at Scripps, and Charlie has been instrumental in introducing me here, but also taking me out to lunch. And as Ram mentioned, you have to accept the lunch invitation with Charlie with some trepidation, because you know the conversation is going to move to some topic that we should do work on collaboratively, and then you'll finish lunch, and then a few days later, 40 pages of draft will arrive in your inbox. And I feel like a very large amount of my time in the last 5 years has been spent working with 40-page drafts that start with Charlie. And my job is to go from 40 to 2. And then along the way, Ram and Charlie somehow decided we should teach a class together, which we do periodically, on how to think about the climate problem. Charlie then decided it should be videotaped and turned into a MOOC, a topic on which all of us were skeptical, and Charlie just ignored us and did it. And now thousands of people all around the world are watching this thing. I was in Muscatine, Iowa in the middle of the winter, don't ask, and giving a talk, and 6 people in the audience put up their hands and said they had watched the whole MOOC, and then started drilling me with questions about what we had said. A lot of us are worried about the climate change problem, and we're frustrated by the lack of action. I really appreciate Ram's talk to try and focus us on mitigation and what you can do about this problem. And I think we're all in the scientific community thinking about how can we help, what can we do? And clearly one role that the scientific community plays is in nailing down the science. If we disagreed massively about fundamental aspects of climate science, the case for doing something about it would be harder. So we've played a role there, and I've been heavily involved, many of you also heavily involved, in the Intergovernmental Panel on Climate Change, IPCC, and trying to put together the science in this area. But frankly, the science that you need to know in order to develop a case for action has been known for quite a long time. The uncertainties have not been zero. They've been significant. In some areas, they've actually gone up. The more we learn about complex systems, in some sense, the more we know what we don't know. But that's all to be expected. And I think really, when we think about how the scientific community can play a helpful role here, it's increasingly less about nailing down the science, the fundamental science, and more about what can we actually do, what can we expect, how can we steer political efforts, and so on. And that's what I want to talk about today, especially with regard to setting goals. I'm a political scientist. I run a lab that studies international law and regulation. And one of the most important roles of the technical community, and this is true not only in environmental agreements, but in arms control agreements, a variety of other areas, is to help provide a compass, not because governments then follow it lockstep or slave to it, but because it helps point people in the right direction. And Charlie and I have been exactly to the model. Lunch which I think I paid for actually, 40 pages, and now 2 pages that'll come out in Nature in about 4 weeks, timed with the Secretary General's conference on climate change in New York late September, have been rethinking this question of goals. And this came up already before the lunch break. Charlie mentioned this, and people have been talking about the hiatus or the pause in observed atmospheric warming. And but if the situation's actually worse, and I think we need to have a complete rethink of the right kinds of goals for climate policy. For the last decade, the official goal has been 2 degrees. And we like to think that we in the scientific community had a big role to play in that. You know, we did all this research, people looked at the research, they said, oh, the right number must be 2. The reality is we had very little to do with it. 2 was chosen because it's bigger than 1, smaller than 3. 1 was hard, 3 seemed scary, and the Europeans were pretending to be doing 2 anyway, so let's just do 2. And the Europeans adopted 2. They put it into law, more or less. Then everybody else started following along, and we're off to the races. And along the way, people pretended that this was rooted in the work of the Intergovernmental Panel on Climate Change, but in fact, when you go back and look very carefully, the IPCC said nothing of the like. But that doesn't matter, because once enough people say something, even if it's completely wrong, it becomes kind of truth. And that's where we stand right now. The new round of negotiations that's underway right now, leading to a big conference in Paris in 2015. Countries are very good at saying we're going to host the ultimate conference. They're not very good at actually getting things done, but this time the French, the Parisians in particular, were really thrilled about this, so they put in a bunch of money, and they're going to host the big conference that's going to lead to the new treaty. You may remember that Copenhagen tried to do something similar when Ram and Charlie and I started writing things together. That didn't work out so well, but things are looking at least a little better now this time than before. But the official goal remains 2 degrees. And this is a serious problem. It's a serious problem because it's organized a huge amount of scientific research about how you meet 2 degrees that has, frankly, increasingly disconnected from any reality on this planet. This is a slide that comes out of the new IPCC report on mitigation. I was the lead author of the first opening chapter and very heavily involved, for better or for worse, in the summary for policymakers. Summary for policymakers this time around had a huge amount of highly relevant political information about how countries organize themselves and so on, and therefore countries were really upset about it. And they stripped out basically almost all of the useful technical information about how we actually organize and design policy from the Working Group 3 Summary for Policymakers. One of the key insights from the new Working Group 3 report, though, is when you take a very long sweep picture of time, going back, in this case, the middle of the 19th century out to the year 2100, these are results from all credible published so-called integrated assessment models. So these are models that have information about the technologies that are available, economic growth, population. The point that Ron made earlier, that this is really a technological problem and a consumption problem and not a population problem, is clear, abundantly clear in the data. I think a generation ago, we all would have talked about how terrible the population problem is now. My own view is in the next generation, we're going to be talking about not having enough people. But the real problem in climate is consumption and technology and the lack of adequate technologies. We were asked to explore the feasibility of 2 degrees. And when you tell modelers with optimization models, go tell us how 2 degrees is feasible, and you give them 100 years, their models can do almost anything. And that's what these different lines show. The blue bands are model runs that are consistent with a better than even chance of stopping warming at 2 degrees. We actually know almost nothing about the real climate sensitivity because of the pause problem, but we ignored that. So that's a good chance of meeting 2 degrees. And what you see is a huge number of runs that can actually do this. And then when you start looking below the surface, there's a lot of kind of inconvenient problems here. For example, the technologies, Jay Apt will talk more about this, the technologies that are consistent with cutting emissions in a way that's appropriate for 2 degrees. The dominant technology is something called bioenergy carbon capture and storage. This is where you grow plants, which sucks CO2 out of the atmosphere. Somehow you drive around and harvest them and don't produce any emissions. A miracle occurs there. You get them into a power plant, you burn them in a power plant, you have a bunch of technologies that capture the CO2 and then inject it underground. It has negative emissions. It just sounds awesome. There are no commercial plants in the world that actually do this. No serious person who has any financial sanity at all is thinking about investing in one. But nonetheless, the models love the technology because the models think that if you just pour money into the technology, the costs are going to come down. And so all these optimization models pour money into these kinds of technologies, the cost come down, and then we're off to the races. And the same story gets played over and over and over again. We've done done some work trying to understand the transition pathways. So this is a pullout of the same information, just looking out over the next 20 years. Compares these scenarios, the blue scenarios, which are the ones that really get you 2 degrees, the yellow scenarios that might or might not, and the Cancun pledges. These are the pledges that governments made to each other after the disastrous meeting in Copenhagen. Nobody actually knows which of those pledges will be met, but some fantasy will occur, and governments will make an effort. And those pledges are themselves already not consistent with what you see on the ground as needed to get to 2 degrees. Maybe they're consistent with some of these scenarios that involve a kind of even chance of 2 degrees, maybe not, but that requires full implementation. And you can see when the modelers are really allowed to stretch their wings, here are some scenarios where I pull out just the runs that allow delay. So you can see some runs that go up, and up, and then they crash. Those are the scenarios where you tell the model you can go build as much of any technology as you want. What do? They build a nuclear plant in every backyard and a whole lot of bioenergy, carbon capture, and storage. I think people often say that economics is the dismal science. I think political science actually is the dismal science. A huge amount of what I've been doing over the last few years is unfortunately been trying to explain why things we've been saying we're going to do, we're not actually going to do. And one of those is the 2-degree goal. And so when you put together the underlying scientific information that Charlie and others have talked about on the pause, and you put together this new reality that even if governments make serious best efforts on their own, all that doesn't add up to 2 degrees. You end up with a very different picture. So I think we've got a combination of problems. We've got a political problem that doesn't, in any plausible scenario, lead us to stopping cutting emissions in ways that are consistent with 2 degrees. And then we have the technical problem related to the pause and other ways of thinking about real stress on the climate system that people have been talking about before. Very briefly, the paper that Charlie and I are writing lays out the case for thinking about better indicators. I think one of the things we might discuss at this conference is, are we ready in the scientific community to outline a series of technical indicators as well as political indicators that are better connected to the reality of what governments can actually do, which is what I study, and what real stresses are being put on the climate system, because average atmospheric global temperatures are a very bad measure of real stress on the climate system. Better measures are ocean heat content. Are we ready to measure that in a systematic way? Top of the atmosphere, radiation imbalance, and a variety of other things that other people in this meeting know much better. I want to just close by saying one thing. It's really not just about goals, but it's about the kind of reality as I see this issue as a political scientist who's spent a lot of time, 20+ years, working with climate scientists in various ways. When you think about the underlying political logic of the climate change problem, mitigation is essential, especially mitigation of CO2, as Ram said, and politically really, really hard, because it requires people to spend money today that gores the interests of well-organized existing interest groups for benefits that are uncertain in the future and accrue globally. We don't do, and problems that are structured like that, we rarely deal with seriously unless they're somehow proved to be a lot cheaper to deal with through technological change. That's why we really seriously address the ozone layer problem. Adaptation, though, is different. Adaptation creates local benefits, and it responds to local crises and so on. And so I think what we're going to see in the real world, and this is the last point I'll make, is that the real world compared with the optimal world, and we in the scientific community are prone to think about optimality, the real world, for political reasons, is going to under-mitigate and over-adapt. And that means the logic that Ram talked about in the paper that Ram, Charlie, and I worked on about institutions for adaptation, that is the world we are going to face because of this deep underlying political logic. And along the way, we in the community, I think, can play a much better role in helping to frame real goals that real governments can actually implement, as opposed to fake goals like 2 degrees that sound great, but in reality don't have any practical meaning. Thank you.
I'm Jay Apt, and I'm here to wish Charlie a happy birthday because nobody else has. As some of you know, his birthday was actually the 20th, if I remember right. So happy birthday in arrears. I like that. Well, that's good. So I'm Jay Apt. I'm a professor at Carnegie Mellon University, a colleague of some of you, including David. And I want to talk to you about a little piece of the problem. A little piece because it's about 40% of the greenhouse gases in the United States, and a little piece because it's the United States. And while I don't believe that all politics is local, a significant fraction of politics is local. And being an experimentalist, not a theoretician, I think in detail about things that I can get my mind around. And so I'm going to talk about the U.S. electric power system and climate mitigation, because that's what I've studied for a bit more than the past decade. So first, let me convince you that electric power is worth paying some attention to. In the U.S., electric power is about 40% of our total primary energy supply and about the same amount of our greenhouse gas emissions. It's been going up. It may have stabilized a bit at the moment because electricity is a preferred means of using energy. My home in Pittsburgh has a coal burning furnace that is there from the 1950s, but we don't use that anymore, right? And that's actually a good thing. So it is a large fraction, and if we go to electric vehicles, it may still be a growing fraction. But electric power hasn't done a tremendously good job at decarbonizing. This is a metric of pounds of CO2 per megawatt hour, which is the regulatory unit, from 1950 until the present, and it has shown modest decrease. Now, I say modest, but the widely loved goal of California's implementation legislation doesn't quite reach where we need to be, which is down here, right? We need to be down around 400 pounds per megawatt hour, and here's the SB 1368 standard, which isn't terribly ambitious. And it isn't terribly ambitious, especially when measured against the technology that exists and one can buy now. The very best natural gas plants around, made by Siemens and General Electric, are down here. And so I would say that we have, from a technology standpoint, a fair bit of headroom that we can advance. But my friends in the electric power system, who like to be left alone, they don't need no stinking regulations, would have you believe that things will get better. They won't get better in time. Here's the same graph extrapolated, and those of you who can read the x-axis can see it gets down to where we need to be, not very fast, right? So the questions are, what do people do, and why did they do it? I leave the why mostly to my friends like David, but I'll give you some reason for optimism and some reason for pessimism as well. The first question is, in the 1 billion that Ram talked about that caused that huge increase, can demand response do the job? We've been getting much more efficient. In the United States, our industrial electric demand is basically the same as it was in 1994, despite the fact that industrial production has gone up by 52% since then. So that's very great efficiency gains. We haven't seen the same gains in residential or commercial units, but demand reduction itself, although it has paused our growth in electric power use, can't do the job on its own. We grew exponentially in this country at 7.75% per year from when we started taking data to the 1973 oil embargo, and then started growing linearly after that. The last 7 years since the recession started have been very different indeed. And so we don't really know whether that's going to stay static. Population in this country is not going up by very much, it's going up by some, and we're seeing some efficiency measures, not nearly what people have done in the industrial area, but we are seeing some efficiency. But even if it stays static, it's not going to get us down to the 400 pounds per megawatt hour we need just by changing the number of megawatt hours. Right. So what have people done? Well, people have gone to renewables, and I'm here in California, and we love renewables. I lived here for about 3 years, and I want to show you what the fraction of renewable energy has done in that same time period. Here is renewable energy, when I was born in 1949, was a bit more than 30%. It got diluted by increasing demand, and here is the growth of wind power here, right? Not the kind of things that you would believe if you read just the popular press. I'm also here to tell you that renewable and low pollution are not synonyms. Our low carbon electric power during the same period has looked like this. What's the difference between these two curves? Nuclear, exact. And so this, of course, is this increase right here due to additional wind. Solar is too small to matter. I'll show you that in a moment. The nuclear build-out dramatically increased the amount of low pollution power that we have to just about what we had when I was born in 1949. This is what the pie chart looks like at the moment. Coal, natural gases, the 65% of ROM's chart maps into emissions here. A little bit of oil, Puerto Rico and Hawaii mostly, 20% nuclear, and then the renewables, hydro, wood, which is mostly pulp and paper, wind, waste, geothermal, and solar. If you were to ask the average person in the supermarket, they would think that the largest slice of this pie was solar. Right, okay. So, I have another question for you. What is the largest change in U.S. low pollution power in the last couple of years? Natural gas. No. It's the 5 nuclear plants whose announcement of closing happened with about 5 gigawatts of capacity. That's not the end of the story. There are 6 other small plants with another 4.5 gigawatts of capacity that are in states with pretty low wholesale electric prices. So they can pay their mortgage, but they can't pay costs for big things, new steam turbines and so forth. And there's another 5 larger ones also in states with very low electric prices. So natural gas has driven the price down. But let's do a little math. That's a total of about 15 gigawatts. There's 5 plants under construction in the U.S. with about 6 gigawatts. They're all, by the way, in non-competitive states, traditional rate-based regulation states. So net loss could be more or less 9 or 10 gigawatts. Now, the nuclear plants generate 90% of their nameplate capacity averaged over the year, whereas wind plants are about round numbers, about 30%. So the next loss would be equivalent to just under 30 gigawatts worth of wind power. That's about half of the wind power we've installed. Here's the graph showing capacity additions into the red total wind in the U.S., about 60 gigawatts. So it's pretty likely that we will knock off about half the gains due to wind power by the shuttering of nuclear plants. I don't want to leave you with the idea that I'm a nuclear proponent. The nuclear industry has not endeared itself to either the financial or the public folks recently, and we'll see how the new nuclear plants do. But the facts on the ground are these. So there are a bunch of states that have renewable portfolio standards of various stringency. Hawaii the most, because they're trying to get rid of the fuel oil, up to 40%, although it's not for a long time. And you know, in here, when you add up the wind and solar power that's required to meet those standards, it'll require about 50 gigawatts of additional wind and 13 of solar. That's equivalent to about 20 gigawatts of nuclear. We've got about 100 gigawatts of nuclear. Much of that's going to age out. Even if only like 20% of it, we're just going to break even with the renewable portfolio standards. To me, that's eye-watering, and it says we have to do quite a bit more if we want to get there. Now, I'm a big proponent of wind and a lesser of solar. In fact, we've just last month published a book on integrating wind into the electric power system. We're about 4% wind. I think that could become 20 or 30% before land use issues get in the way. And as we've seen in Europe, Heinz will tell you in Germany, we can do now only offshore wind. It's the same in Spain. And about 20% is where people stopped stomaching it. But that leaves a huge gap. Even if the wind goes to 20%, and even if somehow nuclear retains its current market share, this is the market shares over time. This is the last 2013 data. And even if this piece went up to about here, that's a pretty big gap. And I can't see filling that gap without using the U.S. fossil fuels. Fortunately, CO2 capture plants are under construction, and Southern Company has a 600 megawatt plant, and Sask Power has a 100 megawatt plant that will start up in the next year or so. I'm also confident in industry's ability to innovate. This is a graph of the patenting ability, patents that are relevant to sulfur dioxide control. What's the big jump? Regulation, exactly. The 1970 Clean Air Act, right? So patents respond to regulation. So what I'd like to leave you with is that we need a mandate to reduce pollution. 111D isn't perfect, but it's a start. It's unlikely that the power sector in the U.S. is going to control CO2 with energy efficiency, wind, solar, and nuclear. CO2 capture from fossil plants is feasible. We need to do a lot more development, and we need to learn how to lower the costs of it. It's going to take 2/3% of GDP to clean up CO2 in this country, but that's about what we spent on the Clean Air and Clean Water Act. And so I'd like to leave you with a positive message that that's something we did and we can do it again. So thank you very much.
My name is Bruno Coppi. I introduced myself yesterday. I have known Charlie probably longer, or at least two people know Charlie as long as I did, since the time he became a graduate student at Princeton. I was a postdoc there. So it's a good opportunity for me again to renew my congratulations for his careers, everything he has done for us. We were together, let me repeat again, in Trieste for a full academic year. It was a summit meeting on plasma physics, where we had the best brain working on this field from around the world. So it's an experience that we cannot forget. I shared with Charlie also interest in space physics, and that he has maintained over the years. Now, let me say that probably you don't know, I have a double degree obtained in Europe. One is in engineering, and I use it to build machines from time to time for fusion research. But also, I was invited by my colleagues in the Cambridge area to set up a so-called Boston Energy Forum. We had money for that, I mean, modest amount. It's made of an outstanding group of people concerned about energy, climate, and so on, about the issues that have been discussing in these days. So many of the things I will not speak for a long time that we are concerned with being discussed, and I'm glad that Jay gave some basic numbers. We have some disagreement with our conclusion, and I will tell you very bluntly, what our conclusions are. Clearly, one of the challenges that had been stated here rather bluntly, for example, by Peter this morning, is that we have to get rid of the CO2. Can we get rid of the CO2 in the atmosphere as it was proposed? I think that is daydreaming from the technology that we know now. We may consider getting rid of it in the ocean, but this is something we will discuss in the Boston Energy Forum. On the other hand, we can do a lot, like Jay mentioned, about reducing the CO2 that we produce and changing our way of living. The other problem is to provide energy for the world population that is increasing. This is what concerns our group. There is another thing that concerns our group, and you will see there, distinguished member of the scientific community there, is that we communicate very poorly with the leadership of this country and of other countries. Many members of the administration come from the Boston area, so we have direct contacts. We discuss bluntly with them. And I think Charlie anticipated some of this difficulty this morning. For example, the fact that this community presents their models in a rather deterministic way, too certain of what they say without arrow bars, that is something that in the administration is not well seen. For example, something that is being said to me rather frequently, they said, Bruno, you are interested in plasmas for thermonuclear research. They're very simple. They're a system of many particles, electrons, and nuclei, very simple. and you discover all sorts of collective modes. You could not predict them. How can you believe that the climate people, they have far more complex system, they can make predictions that we could use, for example, for energy policies? Of course, the administration is interested in what we can say about the climate and so on, in order to decide what to do in terms of encouraging doing research, for example, new energy system. Now, before I show you my very brief presentation, let me say that the investment in new energy sources is insufficient from all point of view. I think Martin Rees agrees with that. That is true at the international level, and it's also true at the US level. So I think I hope we will discuss these issues and see how we can improve the situation. There is something, you speak about mitigation, they speak about resignation, Simon. Somewhat we cannot do anything about climate, and we let the situation drift. This is something which I don't think we should accept. So let me go back. I think I have only 2 or 3 pages here to show. Oh, sorry. Yes, this is a group of people, most that compose our group. You can see there are people from Harvard universities, MIT, and Boston University. They are experts in physics, nuclear engineering, earth and planetary science, and so on. You may recognize a number of them. I will state bluntly what some of our conclusions are. Not everybody is in agreement with them, and I will tell you where the disagreements are. But this group is somewhat, coherent in its thinking. Okay, now the climatologists, expert on climate from our group, ended up by making a published statement. And let me see if the signatures are together with people from other institutions. What do they conclude? That basically the most reliable way to take care of the CO2 production is to resort to nuclear energy. As blunt as I can be. But now there is a problem. The nuclear technology that we are able to offer is outdated. I mean, it goes back to 1965, 1970. And that is a major obstacle. Now, the government should invest in new type, let's say, of fission energy. And some event that was quite, in a way, disagreeable was that we had been pushing for the so-called small modular reactors. They could be spread around the world. You know, this technology taken from nuclear submarine. John knows about that. And there was an initiative by Babcock and Wilcox to produce 200 megawatts, 180 system. The initiative has been abandoned. There is another group and so on. So we think that this is deplorable. DOE has a kind of proposed budget to invest in this area, which is completely insufficient. I could tell you the very few billions. And so this is where we intend to have an influence in Washington to invest in new energy sources. Now, what about renewable? Well, it was mentioned by Jay previously about the German experience. There is a big American report on the German experience on converting to renewable. It was not a happy experience. And maybe Heinz, who is German, can tell something about that. So, going to wind and so on, it will be quite a challenge, and it will not be easy, basically. Now, I'm almost finished, basically. The nuclear engineers and physicists of this group have come up with a document that let me show here that has been quite well accepted. And let me say that this point of view has been accepted by the New York Times. And so although it may be unpopular to speak again about nuclear energy, new nuclear technology and so on, but this is what we think, in practice, this is what we think can be done. So basically, I have 3 questions to pose to you that have been posed to us. One has to do with the presentation of Charlie. Are the models that are made for climate change and evolution and so on convincing, really, to the scientific community when you take the error bars into account, the limitation and so on? Is the climate community, maybe aware of what has been done in other fields in terms of simulations and so on? We have heard a little bit about simulation, but not enough. I think we have to give an impression of being more scientific, basically. And I would like to hear your point of view on that. The second one has to do with the attitude of resignation that exists in the present administration, letting things go. What do you propose that we should say as the scientific community? And the third question has to do exactly your reaction to the German experience on converting from nuclear to renewable energy sources. Excuse me?
Would you summarize the German experience?
Well, there have been lots of difficulties. Sorry, all sorts of difficulties, because it did not, this conversion did not imply simply shutting down a reactor and turning on the wind. First of all, a great deal of these new energy sources were developed in northern Germany, where there are no mountains. You could not store the energy into, basins and so on. The grid has to be a grid that is compatible with a variable energy source. There were all sorts of difficulties that are on this report that would be able to. So then you come out with the feeling that before we think very optimistically of converting to renewable energy, although it's clearly an important thing to do, that the difficulties to overcome are quite severe, actually. And maybe I could ask Heinz to, sorry.
So why don't we conclude with that question, and then I'd like to open it to
Right.
across the whole panel. I don't want to spend, we don't have any.
I would like to say a few words.
In the interest of time, we have about 10 minutes before the break. I want to make sure that the audience has a chance to ask the questions they're interested in of the whole panel, and so I want to open it to other questions as well. I actually have one. I'm not sure that the German solar experience or renewable experiences is the only question people have. So if I'd like to invite the other speakers to come back up, and as well, if you want to, I'll take a seat over there. Nobody really mentioned the issue of putting a price on carbon and economic incentives to move consumption in the direction that it needs to go. And I wonder if that's, and Ram talked a little bit about money and the economics of the stoves and Project Surya, but as a policy objective, setting goals, what's the role of economics and putting a price on carbon? Jay?
I think there is no serious student of this that disagrees that a price on carbon is the economically most efficient way to do this. I will turn to the twin political scientists here for a comment on its feasibility. My view is that that is very unlikely on this planet.
I'll just say very briefly, I'm actually somewhat encouraged about the political feasibility, because the people who want carbon taxes, and there are very good economic reasons why carbon taxes instead of regulation or even cap and trade are economically the right way to go. The people who are serious about this as a policy instrument have realized that you can take what is otherwise toxic politics and make them less toxic by focusing on all the money you earn. And the key to the politics of a carbon tax is a strategy for redeploying the money. And this is one of the areas, although Australian politics is screwed up for other reasons, right now on climate. This is one of the smartest things the Australians have done, is they had a really smart strategy about recycling the revenue. So I'm actually optimistic about that. All that said, there are still strong political incentives to use regulation instead of taxes, because the very reason that economists love taxes, which is they make everything transparent, is why politicians abhor them as an instrument for getting things done.
Question really for Victor. I'd like to suggest that the main reason it's hard to motivate politics in the public is disagreement about the ethics and economics and not about the science. Because if you apply the standard... Can you turn up the volume? Can't hear it all. I was going to suggest that the main disagreement is not so much about the science as about the ethics and the economics. Because if you apply the standard discount rate, as does the Copenhagen Consensus, for instance, you then pay no regard at all to what happens more than 50 years in the future. And then you naturally decide perhaps it's not worth spending much. Whereas if you take a low discount rate, if you have the ethical view, you do not discriminate on grounds of date of birth, and the welfare of someone born today is worth as much as the welfare of a middle-aged person, then you do pay regard to the effects of climate change at the end of the century. And I would suggest that the difference between the standard discount rate and a policy that takes account of the far future is what motivates differences in attitude just as much as uncertainty about science.
Is this the one? I think that's largely correct. It does suggest to us that we in the scientific community need to then also be doing some work on goals around that are connected back to ethics and justice and so on. There's a very interesting spate of papers that will appear, I think, next month in Nature Climate Change that are going to make another stab at this question. Let me just say, methodologically, there's many difficulties here in addition to political difficulties. One of the difficulties methodologically is we don't know the values of future generations. And so we know our value, or we think we know our values. It's a larger question whether we know how much we really know about ourselves. But when you don't know the values of other generations, then it's easy to say we should adopt very low discount rates. But then the logical extension of that for policy actually can lead to very perverse outcomes. So it doesn't get us out of the woods here. This is actually a very, very tricky problem.
Bruno?
Passing this down to Bruno, let me just make one comment. We all think about the CO2 as the largest piece of the problem. In fact, if you clean up the coal plants in this country, you stop killing between 10 and 30,000 people a year from small particulate matter. That's an immediate effect which we discuss far too little.
Thank you. Just a comment to Martin. With my experience of contact with various governments, including, I would say that people who advise the government very closely, for them, their intention are such that ethics plays a bigger role in their mind and so on, that consideration of discount rates and so on. Whether they succeed with their intention is a different story. But the question of ethics, of going beyond profits and so on, is very much there. So this is why the objection on science comes up rather frequently. Maybe, they're just good intentions, but I could assure you, in my experience, that ethics plays an important role.
Okay, one more question. John?
This, I think, for Jay, but it's good you made the comment about 11,000 people associated with this carbon death problem, as it were, the fatalities each year. I thought the number was a bit higher than that, but apparently...
I said between 10 and 30.
Oh, 10 and 30, okay. I was thinking 19,000. But it is a huge issue. But the question is actually very brief. Isn't clean coal an oxymoron?
I think not. The Kemper plant, which is a pre-combustion capture plant, and the Sask Power, which is a post-combustion plant, both require, for their own industrial chemistry reasons, the particulate matter, and especially the sulfur, which is the large precursor of the PM 2.5, to be down to very, very low levels indeed for the industrial processes to work. The emissions from both of those plants will be really quite low. I'd be very happy to live near either of those when they're working.
David wanted to say something about that one.
In about 2005, I led a research team that started tracking every single one of these advanced coal plants in the world, all the proposals, all the real plants, so the kind of all the way from vaporware to real hardware. And we updated it every year. And what was just striking to me is when you looked out into the future, what you saw, looking at all the announcements at least, was this huge surge in what could have been a big transition to clean coal. Now, maybe that's a good idea, a bad idea, whatever it is. And then people started believing the governments weren't serious about doing something about the problem, and the bottom fell out of that entire market. And so the situation today in terms of actual projects going forward, there's a few here and there, almost all of them with financial bloodshed surrounding them, not all, but almost all. The situation today is that investors lack confidence. This is really a political question. They lack confidence in government's regulatory promises. This is one of the reasons why even small carbon taxes are important, because they're hard to do, so they're a way of governments credibly sending a signal that we're going to do something. And when you're in the business of investing in an asset that has 40 or 50-year lifetime, it's all about credibility. The whole game is about the credibility of the environment, and that is at one of the lowest points I've seen in this whole climate debate.
Okay, with that, unfortunately, we're out of time, but you can continue your discussion at the break. Thank you very much for the panel.
This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
Okay, this afternoon's session is on energy and sustainability. I'm Lisa Schaefer. I have known Charlie for 20 years. I'm one of the people who met him when he first came to NASA. I was running the international office for Mission to Planet Earth when Charlie came in to be the associate administrator. And in the last 20 years, we've spent a lot of time traveling the globe together. I put together a few pictures of travels with Charlie that'll just run in the background while I'm saying a few words. So first, I wanted to thank Ellen for organizing this event with Charlie, but more important, for being a wonderful partner for Charlie, at least through the 20 years that I've known them. I think that much of his success is due in part to your support for him. The thing that distinguishes Charlie from many other people I've known is that he has a huge intellect and a small ego. And as Ray Weiss said very eloquently earlier, he really combines a sense of generosity and curiosity, and has taught me many lessons in the time that we've spent together. One of the things I noted when I was trying to recall all the things that we've done is that there's very little that I could say that was specifically, Charlie and I did this. Fuel consumption by the top 1 billion. I'm going to introduce everybody, and then I'll give you the microphone. So I'll introduce everybody, then we'll have they'll each talk, and then we'll do questions at the end. Ram will be followed by David Victor, who is going to talk about the role of goals in environmental governance and continue the discussion Charlie started before lunch about whether the goal of limiting warming to 2 degrees is the right goal, why are some areas of sustainability governance working well and others have failed, and what the scientific community can do to help. David will be followed by Jay Apt, our astronaut, who will present his views on the prospects for low-carbon electric power generation, focusing on the U.S., what are realistic expectations for wind and solar, given issues related to land use. As a local government official, I now appreciate more than ever issues of land use. How much energy do we need? How can we get it in a sustainable way? What role will CO2 capture technology play to enable the continued use of fossil fuel plants? And then Bruno Coppi will summarize the energy challenges and some possible solutions as seen by his energy group and lead us into our discussion with the audience. So each presenter will have 10 minutes, and then we'll hold all the questions until the end and have a very lively discussion. So with that, it's a privilege to introduce Professor Ramanathan.
Thank you, Lisa. I have an experience with Charlie, which I think is unique. When he stepped down from a director of Scripps, I think I was one of the top beneficiaries of that. He moved into an office around the corner from mine, and that started a collaboration, which has been really exciting for me. And then I had the fortune.
Because everything was a joint effort with many other people and much shared credit and shared participation. Charlie has a style of management that really empowers everyone to be and do the best that they can be and do without worrying about who gets credit for it. And I'm very grateful for that. And if it weren't for Charlie, I wouldn't have moved to San Diego. He recruited me here from NASA. I wouldn't have met and married my husband, who's up there on the balcony, and a lot of things would have been different in my life. So I owe Charlie a lot for the improvements he's made in my life. So when we were at NASA, we already had a committee on Earth observation satellites with all of the space agencies that had Earth observing programs, and he recruited me to come here to Scripps to create a similar organization for the oceanographic community, which became POGO, the Partnership for Observation of the Global Oceans. And we set that up with...
You name it, you get credit.
Okay, I get credit for the name. And we set that up with Woods Hole in Southampton initially, and it is an ongoing organization. At NASA, the Committee on Earth Observation Satellites still exists, and it became the foundation. Charlie really re-energized it into the integrated global observing strategy and the system of systems, and the whole concept of networks and systems is something you've heard a lot in the last day and a half. After I got to Scripps, some of the things that we worked on together, which you've also heard mentioned already, we set up the UC Revell program on climate science and policy. Lisa Levin mentioned the students who went to the climate negotiations this last year. Actually, we sent our first delegation in 1998 from the University of California to the climate negotiations that year in Buenos Aires. Chris Mazel is here, who was part of the delegation to The Hague in 2002, so we still have accreditation for the whole. A current MIT physics professor and fusion energy expert, a political scientist who's the author of a book called Global Warming Gridlock and runs a laboratory on international law and regulation at the UCSD School of International Relations and Pacific Studies. A former astronaut who is now a professor at Carnegie Mellon University and directs their electricity industry center. Did I get that right? And a distinguished professor at Scripps who is one of the discoverers of the greenhouse effect of halocarbons, who helped design cooking stoves and serves as a member of Pope Francis's Council for the Pontifical Academy of Sciences. I'm a political scientist who taught business ethics, and I now serve as a city council member in the city of Encinitas, just up the coast. So this is truly an interdisciplinary panel in the super interdisciplinary, or somebody had a phrase yesterday, mega interdisciplinary? Hyper interdisciplinary panel. Sorry. So our topic, energy and sustainability, kind of sums up our challenge. Energy is central to life, and our patterns of energy consumption and production have put us on an unsustainable path for the future. And you've heard the John Muir quote about how if you tug on a string anywhere, you find that it's connected to everything, and certainly energy is connected to everything. So we will cover the role of government, the energy technology outlook, and the nexus between population, poverty, consumption, climate change, and the bottom of the pyramid, those most impacted somebody reads slow, I guess. Those, those most impacted when we don't get it right. So we're going to start with Professor Ramanathan, who will discuss the bottom 3 billion who have limited access to fossil fuels, yet they are the population that will be most affected by climate change resulting from fossil UC system to send delegations to the climate talks, and that's been a very wonderful experience for all the people who've been involved in going to them. I was part of helping create the Center for Marine Biodiversity and Conservation. You've also heard about a lot. I think I'm the first political scientist at the podium in this forum. We'll have another one in a few minutes. And I also have an MBA, so I brought a little different perspective to the things that we were doing, but I served as kind of the ambassador to the main campus from Scripps and helped build some of the relationships between Scripps and the departments of economics and political science and international relations and the business school. And then when Charlie's term as Vice Chancellor ended and the Chancellor said, go build an environment and sustainability initiative with no resources, he turned to me and said, well, now what? And we said, well, let's go do it. And so we did, and we created the Environment and Sustainability Initiative, which then became the Sustainability Solutions Institute. It became the home for a number of interdisciplinary activities for a variety of reasons. I don't think it exists anymore, but it was a starting point for a lot of cross-campus interaction that has become very fruitful. So as I said, Charlie changed my life for the better. He's also changed the world for the better, and I'm very grateful for that, and happy birthday. So. So getting to our panel. An astronaut, an atmospheric scientist, and an energy wonk go into a bar. Oh, no, sorry, that's not what I'm supposed to say. This session will be presented by an emeritus MIT physics professor who's an expert on fusion energy.
I'm not emeritus.
Excuse me?
I'm not emeritus.
Oh, I'm sorry. By